My name is Peter Pagani, and for my MEMS 5001 final product, I've decided to optimize a muzzle brake for a 5.56 by 45 NATO chambered rifle using the genetic algorithm function in MATLAB. A muzzle brake is a device attached to the end of a firearm which is designed to redirect the expanding gases behind the bullet. When a bullet is fired, the barrel of the rifle acts kind of like a jet engine, throwing the bullet and expanding gases forward and causing a force to be felt in the opposite direction while the bolt carrier group accelerates backwards. Muzzle brakes work to redirect some of the expanding gases again in order to counteract this felt recoil by canceling out some of Newton's third law forces from the expanding gases. This reduces muzzle rise and allows the shooter to more easily stay on target between shots. For this optimization, I'll be maximizing the forward force to counter recoil while minimizing the overall length and size of the device. The optimization parameters will be the number of the baffles, the size of the baffle ports, the distance between the baffles, and the angle deflection. The most closely related research to this topic is a paper by Osama Abdusalam of the Military Technical College in Cairo, Egypt. There, their team optimized a muzzle brake for a large caliber sniper rifle using similar parameters to this project but very different methods. This paper used what they call design of experiments, or DOE, for their optimization, which uses a matrix of 3 objective functions to maximize efficiency and thrust while minimizing felt recoil. This was done using multi-objective genetic algorithm. Other relevant research comes from Cal Zant of PrecisionRifleBlog.com. Zant's research comes in the form of testing various muzzle brakes currently on the market to find typical values of recoil force reduction and their relation to baffle angle. While Zant focused on rifles and brakes chambered in larger hunting rounds, his work can easily be extrapolated to the 5.56 cartridge because these values are in relation to the larger belt carrier groups for these types of rifles. Therefore, the force reduction should be similar regardless of cartridge size. Zant found that the best brakes typically have larger baffle deflection angles, up to 30 degrees, and these brakes can reduce recoil force by anywhere from 300 to 700 pounds force depending on the baffle angle and brake size. From this research, we'll expect our muzzle brake to perform similarly. The model for this optimization is based on a basic thrust equation. However, there are modifications made to the first term in order to account for slight velocity changes in the gas over the length of the brake. The constraints for this optimization will be that the overall length of the device has to be less than or equal to 3 inches. This is just to be in standard with regular muzzle brakes already seen on the market. The second constraint is that the distance between the baffles has to be greater than or equal to half the baffle width. This is so that the program doesn't try to shove as many baffles into the brake as possible without regard for material strength. In addition, in order to satisfy the ideal nozzle assumption that's being made for this optimization, the angle of deflection must be less than 30 degrees. The final fitness function after plugging in all the knowns, as described in the report, is seen below. Running the MATLAB algorithm gives a final thrust value of 500.076 pounds force. This comes with 7 baffles in the brake, each being 0.25 inches wide, with 0.125 inches between each of them at a 30-degree angle of deflection. The generation plot for this can be seen to the far right, where we can see how the successive generations of the algorithm work towards a global minimum until the average change in the penalty value, or the fitness function, becomes negligible between generations. The optimized muzzle brake was also tested in a SOLIDWORKS environment in order to verify the results. As you can see, the SOLIDWORKS simulation gives a final thrust value of 489.71 pounds force as opposed to the MATLAB value of 500.076. This small discrepancy from the MATLAB optimization is likely due to the non-ideal flow conditions which the simulation accounts for that the optimization in MATLAB doesn't. Earlier generations of the MATLAB optimization were also tested in SOLIDWORKS in order to visualize how different designs of the brake create suboptimal thrust values. As can be seen by the force graphs on each generation, the earlier generations have much lower thrust values than the later generations as the program works closer and closer to the optimal solution. In these results, we see that the SOLIDWORKS and the MATLAB solutions line up very well, and they are in line with the expected values between 300 and 700 pounds force. However, we can also see that 7 baffles is a bit of overkill, and the 3-inch length is as well. Most of the force is being imparted on the first 3 baffles, and that's why most muzzle brakes on the market actually only have between 3 and 4 baffles. While this optimization isn't perfect, it has proven to be effective, and it also sets the stage for manufacturers to customize their own needs. For example, future considerations could involve considerations of overall weight and material cost into the design, which may affect some of the known variables that manufacturers play with.